Yeah, just take me a bit. Hello, everybody. Still, sorry, leave it. Oh, yes, this one. Okay. Okay, so hello, everybody. Thank you for coming to my seminar. I'm going to talk about algebraic programming and its application and combination with AI methods. This is the short survey of my past, present, and future research, and my story will consist in 4 parts. It's first is some history of my participation in different industrial projects where the algebraic programming or modeling was deployed. Some survey of theoretical background, story about applications, and the last my exercises and experiments in combination of algebraic modeling with AI methods. So, a couple of words about me. Originally, I'm from Ukraine. I had a postdoc in the United States in Missouri State in Rolla University, and I've been as I worked at Motorola company as project leader and requirement analyst, and I worked at Intel company, and in Edinburgh I worked at the research center of Huawei. Now I'm in the staff of this. So I present the algebraic school of Viktor Glushkov. I'm the follower of this school, and this school has been incepted in the 60s, and the main highlights of this school is a classic work in the digital automata theory. It's one of the first in the world computer algebra system where the symbolic computation has been implemented on the level of machine instruction. This is one of the best theorem proving, automatic theorem proving system, algebra of algorithm and parallel computation. And so I joined to the school in 1999 when the algebraic programming system has been developing. So this is the system which is based on the rewriting rule techniques, the basic of symbolic computation. The special language of algebraic programming has been developed, AppLang language. And it's the difference of this system was that it can use the different strategy, and the user can create the strategy of rewriting, and user can create its own strategy. This system is open and is maintained. Now here you can see the example of a rewriting rule system, example of a planned program. A rewriting rule system, it contains the syntax of system and the together with the some imperative operators.
Can I interrupt on the previous slide? Yeah. So I was checking your code, and I mean some of these I can make sense of, but there's 0 equals 1, and I wonder what that means.
0 equals 1. It's a rewriting rule.
Okay.
0 should be rewritten in 1.
Oh, okay. And okay, at the term level.
For example, don't consider the semantic, because it may be 0 equals 1. Yes, we rewrite 0. It's a special, maybe when they call this RS.
Right.
RS, they may be for special reasons. Yes.
Yeah. So from my understanding, it's important that I understand.
Yes. So on this
writing 0 into 1.
the left side we have the what we write, and the right side.
Okay.
So the algebraic programming system was developed on the base of the abstract data, universal data types. There is a library of processing for processing of abstract data type. It's open and many people use it. It was in the beginning of the century, and following tasks were solved using this system. So first, it's automated theorem proving. It's the first purpose. We create our own SMT solvers. It was the Pressburger algorithm for integral theory, Motzkina-Fourier algorithm, symbolic solver, and bitwise operations, and another special solver that are needed the algebraic modeling. So also it was used in the educational task for task of resolving a polynomial algebra and theory, set theory, trigonometry, and a lot of tasks, a lot of problems we implemented within the Boolean logic. Sorry. Back. In 1999, Motorola company offered the cooperation in verification and testing of requirement specification. And I've been a co-author, and we deployed the verification requirement system at the Motorola, and it was used in the more than 50 verification project in microprocessing, automotive industry, networking, and telecommunication. And this time was insertion modeling system has been created as the extension of algebraic programming system, and our community of algebraic school, we created the insertion modeling paradigm, and it was based on the theory of agents and environments and the behavior algebra. So the theory of agent and environment, it was created by the David Gilbert at City University London, and Letychevskyi senior, it's not me. And it was published in 90th, and this theory was the attempt to present the general theory of interaction as interaction of agent into some environment. The entity of agent was defined that has a type. Its type defined it by its attributes. Agent has a behavior that is determined by the sequence of actions, and the sequence of action forms the behavior. Agent can be inserted into environment. Agent can be environment for another agent, and environment can be an agent for environment of high level of abstraction. This is the first step to provide the multi-level algebraic modeling. So this is an example. The computer is environment for operation system. Operation system is environment for agent program, etc. In biology, in modeling of cells, we use the cells is environment for cells. Organelles is environment for proteins, and so up to the particles. Algebraic behavior was developed in the scope of the theory of agent and environments. It has to. This is the double sort algebra over the actions of agent and behaviors. So it has two operations: the prefixing operation. Prefixing is separate the first action in the behavior, and it has the non-deterministic choice. It establishes the alternate behaviors. So also it has the terminal constant, successful termination, deadlock, and unknown behavior, or arbitrary behavior. And it was extended by the parallel and sequential composition. With the usage of, so we can create the behavior algebra expression, with expression which was created by this operation. And we have also the algebra behavior equation. In the left part is the identifier of behavior. In the right part is the behavior expression. So we can create some behavior system of the behavior expression which can present, for example, the behavior of the program, represent cycles and represent the junction or alternatives, comparing with the known similar algebra like Milner's algebra, CCS. And I can say that the purpose was to create this algebra more general. So Milner, he concerns with the just synchronization and semaphores and other semantics of the message passing, but it's more general, and the Milner algebra can be created in the scope of the behavior algebra. The same is for Dijkstra algebra, CSP, the P calculus, and the same is for mobile ambience of Cordelli. So here the example of system of equation.
So when you're saying similar algebras, actually now what you're saying is that your notion of that notion of the algebra encapsulates the other ones. It can be instantiated to the other ones, right?
No, it means that the similar algebra, yes, it come, of course, it come from it. If Milner created his algebra earlier, and these are the algebras of behaviors. All of these, they describe the process of behavior of program of something, and try to create some operation over behavior. So this is what I mean, the similar algebra, that the algebra over behavior and the operation over behavior and property of this algebra is usually described in.
Is it what you mean? There's more programmable.
Yes, it's
closer to what an engineer would need.
Yes, it's maybe closer to engineer to express the behavior, the hardware, for example. So now what kind of agent types? Agent, as I said, agent has attributes. Agent has type. It's defined by the type of its attributes, and we used in the insertion modeling or algebraic modeling different types. You see integer, real, the bytes, and Boolean functional type. It's a parameterized type, which is, we can express the algebra of three terms. Theory of least, theory of queues, enumerated type. We can create our own type, but you should define the objects and operation over this object. But to use algebraic model, you should have the proper SMT solver for this, and I will talk about this later. As I said, behavior algebra is the double sort algebra, and it's over behavior and actions. Actions are generic, and actions we present like a pre-post-condition for actions of agents. So precondition, it's some predicate of conjunction of predicate of difference theory. And post-condition is the changing of attributes of agent attributes. So agent has state, its state defined by the set of its attributes. And what is the semantic? Semantic of the agent action is that we, if the action, if the precondition is satisfiable, then agent can perform the action in some environment and change correspondingly to post-condition. How to get the next state of agent? So we define the function, the defining state, the function on the precondition current agent state and the post-condition. We call it predicate transformer. This is the notion that we borrowed from Dijkstra. And predicate transformer define the next state, and we should define the predicate transformer for every data types. Here the easiest, the simplest predicate transformer for integer theory. So we have some action with precondition and postcondition in x greater than 0, x changing like x plus 1. current state x equal, we are using the C syntax for assign for equality. We express the old value of x through the new value and substitute it into the conjunction of precondition and current state. So, and we're gonna take we're gonna get the next state. The theory. It's very easy for integer, but it's too sophisticated for the other theories. If you, for example, use the quantifier, we can use quantifier. Yes, a universal quantifier exists. Yes, in the precondition, and so this is very suitable for to express with some subject domain. And this theory was published in our paper, Insertion Modeling and Symbolic Verification of Large System. And we have behavior equation system, for present the interaction of agents. Agents can interact in parallel or sequentially. It depends on the formalization. We have the list of actions of every. We have initial state in the formula over the attributes of the agent. It's not mandatory the specific concrete values of agent. It can be formal, any arbitrary, some constraints or anything. So agent can perform actions correspondingly to behavior equation system. We unfold the behavior equation. The unfolding is realizing in the rewriting rule techniques. We unfold this system, and we will get the new states, and we have the sequences of states. It's maybe a lot of states or sequences of action. We call it trace. So this is the forward algebraic model. It's a forward algebraic modeling. And when to stop, well, we will stop if due to the purpose. For example, we should prove the reachability of some property. If property intersect with the states of agent, some agent, so then we prove the reachability. So the one or the purpose of forward algebraic modeling is to prove reachability. So some example it's from in my industry experience. This example of the protocol of telecommunication protocol, it was the verification of completeness of requirement. The problem in requirements, there are the deadlocks or non-determinism to keep some safety. So what are the requirements for telecommunication protocol? It's maybe they're given by text, as a text. It's maybe thousands of pages, and people, requirement analysts, they create the formalization, create the behavior equations manually, and afterwards we can check when we have the formal model, we can check the completeness formula, absence of deadlock. Formula completeness is that this junction of all precondition is equal 1. 1, it's a Boolean 1. So how to do it? We should prove with UDHSMT solver prove the unsatisfiability of negation of this property. If it is satisfiable, so we have agent state where this property is violated, and then, but it can be unreachable. We should prove the reachability of this agent state, and we start to if we reach. Okay, we have the trace. Okay, we reach. But how to prove unreachability? We should bypass all scenario, all state is time consuming and maybe never ends. For this purpose, we use the next techniques. It's a backward algebraic modeling. We define the backward predicate transformer, the function over the current state and post condition, and we can get the previous state. We use the backward modeling. In sometimes we can go not from initial state to property, but from sought property to initial state. And is sometimes it helps, and we can reach the unapplicable actions. But we should not. Sometimes we should not bypass the whole space of the states. But it's not the remedy. It's not the solution. So for this purpose, we use the following formal method. It's invariant generation. It's a local algebraic modeling around the some states in the computation of invariance with usage the over and under approximation techniques. I will not dive deeply in these techniques. If it's interesting, I can provide the special seminar because we have the publication. When forward modeling, we can face with the non-linear expression and very hard to SMT solver to resolve it, and maybe so we use the approximation techniques, for example, to make some over approximation about the linear. It's a known numerical methods, and then if sought property is intersects with under approximation of state, that it of course intersect with the state. And if sought property does not intersect with the over approximation, of course it doesn't intersect with the state. So this also is some techniques of proving the reachability of property. So we have also lightweight modeling regarding coverage, priority-based search, just for quick detection of reachability, different heuristic, and the techniques of enlarging and factorization. It's very close to abstract interpretation by Quasar, but it's our own algorithm when we can fold the behavior into the action and automatically compute its pre and post condition. Okay.
Can you take the slide before that?
Okay.
Before that.
What before?
Could there be multiple previous states? I mean, is it necessary that it is a single previous state?
Yes, it's previous states, but yes, previous states in the function over the you have current state, you know the action 1, action 2, action 3. For this action you compute this predicate transformer. Okay, the result of predicate transformer is the previous state. If the previous state and intersect with precondition, okay, you can go for further.
I think what you mean is that should it be a set of states?
Yeah, that's what I meant.
Yes, it's a for sets of course.
But in general, if you start in the current state and you invert, can there be multiple states to which you map? And is this then a non-deterministic function? Is that how you use it?
Okay, one, the first, the second.
Or do you get all states?
All states that are possible from this state, that are reachable, they all are reachable. But if you read the next states, so it's not we can define that. What does mean we have the formula of a state, this symbolic state, this is set of states.
Oh, okay.
It's not specific states here. The set is formal over state.
But this is more a description of the set of states. Actual states.
Not a state, it's formula over states, not specific. As you don't consider specific. It's algebraic modeling. It's not imitation. Yes. So let's continue with with very important algorithm which we use in cybersecurity. This is algebraic matching. Before we consider the reachability of the property, but how to prove the reachability of demanded of undesirable scenario in behavior of the system. So for this purpose, we define some pattern of behavior. And this pattern is cover the set of possible. I will give an example later in cybersecurity. Yes, okay. And we provide the matching of this. What is pattern? Pattern, it's also the system of behavior equation, but it consists the arbitrary or unknown arbitrary behavior. And this is a pattern. Algorithm, it is based on the algebraic model, and we should define the example, counterexample, which yes, we have the trace or set of traces up to the preferences of the algorithm. We call it the solving of behavior equation relatively to the pattern. I will show the example later. So now applications. So we dealt with this theory last 15 years, and we were engaged in developing new, improve the old, and the creation of new in deploying in the different in the industry. And this is me and my colleague from Amsterdam, Professor Peszczanek, and my postgraduate and postgraduate and postdoc students in different countries. So I still have them, and the followers of this main participation in some project. So now we are focusing in the deployment of this theory in the industry and combination with AI. So we consider these four. I'm going to talk about these four applications: cybersecurity, hardware, software, verification, modeling, science experiments, so for physics, biology, and chemistry, and the blockchain. The problem: how to get behavior algebra model. So first, in Motorola, we created manually for requirement. It's time consuming, it may be unprofitable for verification for formal methods. So we consider the creation of translation of technical specification to the behavior algebra expression. Here, the example of C program, which was automatically translated to the behavior algebra, to the behavior equations. Behavior equations present the control flow of this program, and the action, they present the semantics of every C operator. So the same things we did for the binary code. Yes.
On the previous slide.
Okay.
So what you say suggests that your specification in the behavior algebra model will be more or less the same size and level of detail as the original C program, or is there also some abstraction going on?
I think no, so no abstraction. It's strictly can be translated.
So they're isomorphic, essentially.
Some isomorphic.
I mean,
yes, but yes, because it's a lot of syntax sugar.
yeah.
And for this we created the insertion. Even create some papers. Insertion semantic of C program. Semantic of C program in behavioral algebra. So we consider how it can present it. Maybe we not need all this diversity of this syntax sugar, but it's enough. It's enough to use the simple data types. It's pure C, not C++. We did not finish.
No, C is fine. Yeah, but, so the thing, what I'm wondering is, so for example, if does this model the control flow graphs of the C program? Is that what it actually models then?
First, it's for control flow, but we have the actions. This is behavior, but we also have the actions, and every actions. But it's too small. It presented as a pre-post condition syntax of C, semantics of C operator presented as pre and post condition. And this semantic, for example, I know the semantic of C in the I don't know, in Microsoft, it was the semantics with usage of the three operations. These machines. I know this presenting of semantic of program language in the as some formal language, which propose control flow as some formal mechanism, but together with the semantics of C state operators. The same thing we did for binary code. Binary code, it's we did the translation of Intel x86 assembler to the behavior. It's almost the same, but we use the control flow, this set of we decided the control flow. It's a behavior expressions, and the semantics of every machine instruction. It's an action. The same things was implemented for hardware. So we have design language, VHDL design language. This is the example how the it can be translated to the. We even consider the binary hardware code. This is the result of compilation of high level of the design language. It's to provide to use the formal methods which can give the more accuracy. And if you have the behavior expression and actions, okay, we can use our algebraic server, our formally. It's more than 50 different formal methods for I will show in the end in a nutshell the structure of algebraic server. Yes.
So do you do this by hand, or do
No,
you write a
no.
compiler that compiles this into that?
Translation is automatical translation of design language into the end.
And how do you ascertain that your compiler is sound?
Yes, it's a
Do you prove your compiler sound? Is that something you do as well, or?
Yes, we first we create the formal semantics, and we prove. We do not prove it formally. We do not. We test it. We test it because it's a big work. We have no time, but maybe it's maybe useful to create that this presentation is equivalent to the presentation of VHDL specification. We ask especially the reviews.
So is it the whole of VHDL or is it a subset?
Subset. We did not finish, but the subset it was created for the nuclear plant for the device. Yes, and that it was enough. Yes.
Yeah. So which kind of hardware properties are you trying to verify?
For hardware, okay. First, it is vulnerability. It's possible overflow or possible. Signal races is the main thing that should be detected. But when I worked in different hardware company, so they asked to prove the annotations, the assertions, some assertion that technical specialist prepare in the code. So he must be such properties. It has to be proved.
So they're more like domain-specific assertions.
Yes, of course.
Specific, yeah.
Yes, of course.
Not generic.
Safety property or annotation or contracts, something like this. It's of course it's domain-specific. So the next cybersecurity. I reached the application. So cybersecurity, this is the example of the vulnerability of in cybersecurity. This is we present at it's a classic attack, stack damage. It's unauthorized writing over the stack boundaries, and it can cause the damage of execution, or it can equal. It can also intercept well, the interception of control of the program if you write in the return zone of stack. So you can see this is the some patterns which start from the intrusion. Intrusion can be from keyboard, from socket. It with the analyzing of the machine command syscall. It's a lot of different kinds of this command. You get something from outer space. Then it presents the allocation of stack and the writing out of the boundary unauthorized writing. So we can see this also. We can add the action with some constraint which are suitable for us, because, and we have this. We have the behavior equation. So how does it work? So we get the binary code, disassemble it, and convert to algebra model. We have a database of algebraic pattern or vulnerabilities, and we provide the algebraic matching algorithm and find the example of the trace if you detect it. And the main things we can define the data exploit of the data that can be input to that vulnerability triggers. Another kind of usage of algebraic modeling is used in the real time, but in real time it's detect to attack. But real time is much more complicated, because should we again the input is the traffic. We quarantine traffic and we analyze this traffic correspondingly to the we model this data on the model of the system to be which we try to defend. We should find 1, 2, 3, 20. How many patterns we should? It's a long time. It will cause the non-stable work of networking. How to overcome it? We use the AI. So this is the neural network. It was training on the. It's well-known techniques. It exists on the examples of attack. It classifies the attack, and in the case of intrusion, neural network accept first the traffic and classify it and give the clue to the algebraic and to the algebraic component, and then it check the only or just one pattern. And in this way we activate this algebraic component only when we have suspicious behavior. Fast analysis neural network will do much faster than algebraic component. Of course, it's a lot of questions here, but we have now the prototype on one of my post graduate. He created this create the system that work, and it's really it can help. And yes.
So are you now using the neural network to kind of pre-select what possible attack patterns are most likely, and then you only formally check for those?
Exactly. Just only when it's suspicion. But the problem is that a neural network, it's a lot of false positive. False positive. Like, for example, if you try to detect, to classify the anomaly, the behavior. And the other problem is the adversarial attacks. So I think it could help, because we prove that it is by algebraic component that it is false positive. So this is some experiments to move to create the really intrusion detection system.
So is the idea in a long time it would be a real time?
Yes, yes, algebraic. It's because we use solvers. It's a long story. So the next blockchain modeling. The blockchain modeling was interesting experiments, and we apply algebraic modeling for analysis of consensus algorithm for smart contract vulnerability detection. But the most interesting result we got when model the cryptocurrency project and the behavior of cryptocurrency or cryptocurrency economy. Cryptocurrency, it's called token, and so this is the token economy or tokenomics. So this modeling of tokenomics and analysis of its properties, it's very important for the project. So we present the agents of tokenomics as a trader, investors, and consumer of service, suppliers of service. They can buy cryptocurrency, sell cryptocurrency, hold, get rewards from platform or different special service. It's a farm and staking. It's these terms of blockchain of the cryptocurrency project. But we can analyze for the equilibrium of tokenomics. We can analyze the danger of centralization. We can also check some constraint over the price of tokens. And we can also verify the malicious actions or the possible malicious actions of the agents. The next interesting experiment, just in a nutshell, it's modeling of experiments in physics, chemistry, and biology. We define the agent on different level of abstraction. The atoms, it contains the attributes like the number of protons, neutron, mass attributes. The same is for molecules. Molecules have another attributes on another level of abstraction, and also for virus. The number of proteins and his carbonic drag, mass, size, and very specific that biologists know. We can define the actions between these. The action is the creation of bond between two atoms, between atoms and molecule. Or this is the example of ionic. It's from my last presentation on the Virology Congress in London. I use these slides. So this is ionic bond, covalent, non-polar bond, different bond of atoms or molecules. The next, it's we can do it for proteins. Proteins can contain in the list of data types. It can contain the type of agents, also at the types. So we can. But in the modeling of experiment, of course, it's not interesting to work with the single atoms, so we consider the substances, the quantity of substance in mole, and use the differential equations for. It's a continuous process. We use the differential equation, but it's also the one or the feature of. And we try to add it to the algebraic modeling, but it works when we can solve the equations, or create the differential invariant. So this is one of successful application of algebraic modeling in biology. This is the usage of vesicular stomatitis virus. And penetration of this virus, and it can cause the death of tumor cells. This virus is not harmful for human and use to kill these cells. So this is the trace. This is the set of agent actions. It's different to increase concentration, increase temperature, consider the state of the another organelles in the cells. So we consider the different events that can cause this apoptosis process is the death of tumor cells, and we create this trace, this scenario that can lead from penetration to the apoptosis on the level of quantum interaction, because on the level of viruses or chemistry, it's impossible to model. Okay, now just okay, this last two slides. It's usage of AI together with modeling. Of course, the algebraic modeling we can face with the combinatorial explosion, especially in the modeling of experiments. So how we could help? So this is the first experiment. We were inspired because it was successful. So this is the writing system. It can prove some theorem in polynomial algebra. So it proved the equality F is equal G. How to prove? We should apply the theorem, the list of theorems at axiom, and to get G formula. We define the relation closer between two formulas. This is the number of proving steps when one can be obtained from another. We create a data set. First of all, we generate a lot of different successful proving. And we borrow from the prover competition. It's a TPTT environment. It's open. We can get this, and we automatically create these data sets. Inputs of the neural network. If the two formulas, the output is this relation between this formula. And when we prove the formula and each step of proof, we choose. We have on every step of proof we have the options. We have the options which theorem of axiom we can apply, and we choose those theorem, those writing rules. After applying of which we get the minimum relation explodes, and we get such picture. Of course, that was some, but very non-significant number of the redundant application, but we do not provide the bypass. But of course, it was implemented on the very restricted set of formulas, because we use the DNN, and so but it's better to use the maybe graph or convolutional, and because the formula can be have a very different structure. But for the first step, we did the first step, and it was very interesting. It's semi-manually, of course, because it's not the system, but it was this first result. So the same thing. The same thing we tried. We're gonna try for biology, where we have also a lot of options on the every time of modeling of physical, chemistry, biological process. But we define the relation close between two states, the states of agent and the states that we should to find. For example, in finding to find this some state that presents some new substance. Now we have a lot of neural network that can create a new substance with the demanded properties, but algebraic modeling, but we don't know it's really corresponds to this property, and biologists or chemically should double check this. But if we provide algebraic modeling, we have the proof evidence that these results will satisfy to the property of the sought substance. So it's 50 minutes, sorry. This is the last slide. It's in a nutshell, all technology, we have the front end, some translation, automatic translation into behavior algebra expression. We have insertion model creator. It's a special tool where we can create the agent, create the actions, create the behavior, and to connect manually, but with much better than to. But in this idea development environment, and then we can call the algebraic server. It's a set of different formal methods, and we try to add two new possibilities. The first is we collect all algebraic modeling artifacts for future, because we have more than 50 formal methods that can, for example, prove reachability or safety. And then using this future neural network, we can select the proper method. The second is a possibility to create your own methods using a plan, create your own algebra, and create your own input language for usage of the existing algebraic servers. It's all open and it's for exist. We can share it. So it's all my story. Thank you very much.
Yeah, so if you go back to your slide on the biological, the previous slide. So no, I think this
This one.
let's take this one. So no, maybe the apoptosis one, maybe that's better.
Okay.
So it's like you say, well, you can maybe use your system, I guess, to prove now that introducing whatever leads to this apoptosis process in which tumors can be killed, right?
Yes, we present.
Yeah, so you can present that a path a trace exists that will lead to that situation.
And what?
Yeah. But on the other hand, it could also be because I can imagine this is very non-deterministic in general. So it could also be that although there is a path there, in reality, it may not be a very likely path.
Yes, of course.
So what could you add something like probabilistics to it, that you can say, well, if you add maybe more of this, or if you increase the temperature a bit more, then you increase the chances of a particular state arising? Is that?
Of course, you can add the probabilistic rules for this, of course, it's cover all possible. Maybe with a very low probability. Yes, I understand. The problem is to prove that such scenario exists. Of course, you can add probability into the actions, and the actions of agent it will work. For example, yes, really, it's not realistic. So let's consider the probability. The problem is the problem of the who is the user, because how he knows the probabilities.
Well, I understand, but I think if you would look at the other problem, is that, for example, you want to prove that an interaction does not exist. That is typically easier then, right? Because then you would do not need
the bypass, the traversal of all scenario.
And have you experimented with probabilities, like I suggest?
No, never.
I guess, I mean, the domain has to ask for it.
Maybe, yes, I know. But some people used these techniques, but I don't know. Some used for blockchain, for example, because this may be done. Maybe attack with some probability, and these probabilities are known. If they are known, and we can get it from data or somewhere, then we can really create the great.
Yes. So you talk about modeling agents from AI point of view. Usually, agents we have agents that act as actions and act in the environment. But usually, an agent also has a goal, right? How do you encode the goal of the agent? The goal.
The goal.
Yeah, because agent want to do something, right? Want to achieve something. That's the definition of agency.
Yes,
Don't you?
we have a list of all. In the modeling, agent doesn't know what he wants.
I
And
think this notion of agent doesn't have that.
yes,
Okay.
because this of course if we have the goal as safety condition or liveness condition, we should consider the possible actions
Mm.
if he wants or he doesn't.
Yes, because if you can assume that the agents have goals and it wants to achieve the goal, then you can maybe you can eliminate some.
Select the action that are
Yeah, so you reduce the in some sense.
yes. So some direction, yes, you can give the some we had such tools when we have the behavior equation as a graph. It's a graph. And we go there, don't go there, don't go there. We select the transition. If yes, it's possible, it's interesting. And we had for testing, because for example, we can use it for testing, for example, this model to generate test. But if I would like to test some restricted areas of models, so I should exclude some paths that lead. So yes, it was such. Yes, it is.
Yes, so I guess this is more relevant if you want to models like blockchains, because people want to make money, right? So the goal of the
Yes.
agent will, maximize the amount of money that they.
Yes, but I can express it in the behavior, in the actions, or in the yes, it can be malicious behavior. It can be normal behavior. So then, yes, of course, we can use this constraint to reduce the edge space. Yes, of course, possible. Yeah.
A related question. So usually, inevitably, you end up needing to use abstraction. So if you look at industrial examples, it's either a handcrafted abstraction or a mechanized abstraction. Have you ever come across the need for this or anticipated the need?
Of course. If we have some property, we have the property of safety, we have the attributes, and we have the dependencies of these attributes. And we can really define the area only for this attribute. All redundant we can exclude. So we can exclude, yes, this is a possibility to exclude, to assign some exclusion. Abstraction. Sometime we should analyze the behavior or some level of abstraction. And in the term of the high level, we don't need, for example, to consider the atoms. We would like to consider on the organelles of cells. So then it's possible, as I said, to fold, create some such, or manually or automatically, to fold some behavior into actions and create it pre and post conditions, so we abstract of something. But of course, algebraic modeling, we can assume that we abstract of some attribute. These attributes are arbitrary. We don't know about them. We don't know. We don't create the constraint over these attributes. So of course, we can abstract of them. It allows it algebraic model. It's maybe one of the more significant feature, because we can abstract and to operate on analyze on the some level of abstraction.
One observation. So I don't know if you're aware, a school with Edinburgh has a new CDT starting, reliable and dependable systems. So it's one's PhD students. It feels like your kind of research would be really applicable. It's more an observation for you. It could be quite an opportunity.
Can you take that earlier slide in which you defined the grammar for behavior and action? I mean, it's one of the earlier slides.
Yeah, I think.
Yeah. I mean, where you define the grammar for behavior and action.
Behavior,
I think
this one.
what that like different behavior action like that. So I'm just asking like when you define that, is it like the action and behavior specific to a kind of agent, or like let's say if I have a system in which different kinds of agents are acting.
Okay, yes, good questions. Yes, the behavior is created for I know this what you mean.
Yeah, this one. Yeah, so there is no
Yes.
annotation.
0 equal B1, the one agent, in parallel B2 it's another agent. We can consider 2 agents, 3 agents.
Is it necessary that they are all same kind of agent? Because like some agent can perform some actions, some agent, I mean, if they are like, let's say like different kind of agent. Let's say if you are talking about programs, all programs can have like same kind of action. Let's say programs are some other kind of thing. I mean, not programs. So it could have different actions.
Yes.
So is there any way to annotate that, like what kind of agent we are referring to?
You mean, does it have a type system?
Kind of in the sense that like, let's say if you are like, I mean, let's talk about like a real example in which we have a system in which different animals, and an animal, let's say cat, and cat can perform different actions, and dog can perform different actions. If I define the actions like this, A11, I mean, is there a way to say that A11 can be, is it referring to a cat or is it referring to a dog like that? That's what I'm asking.
Okay. All actions A11 are in the behavior equations. Those, of course, if this action over animals, so it's universal, it's specific for cats, so you create for cats. The main principle of theory of agent and environment, agent interacting environment, agent doesn't know about another agent. He just send something to say, to send message, or send to environment. We have a possibility to send via the global attributes. Send it to environment know everything about actions. You can it's almost the same as in object-oriented programming. So you can create, but there are no hierarchy of classes. You can create the actions, but maybe it will be useful in the hierarchy of the agent. You can create some actions for dog, for some for cat, and when you create the behavior equations, the user should monitor, should watch which is applicable, this is behavior of dog. Okay, I use dog. This is behavior of cats. B1 is for dogs, B2 is for cats. Maybe they some intersection.
And that is not part of the syntax. There is no way to specify each action. What action is? I mean, it's up to the user. That's what you're saying.
Which action? Yes, of course, user-defined action. User defines action. It is allowed to use the parameterized actions also. So if it's for the animals, so you can parameter it's animals action for cat. This is animals action for dog. Yes, this it can be.
Thanks.
But would you model that in the precondition then? Does that make sense that you say I have an action, I only wanted to apply to cat, so in the precondition I'm going to check that what I'm operating on is a cat. Is that the way you would
use it? But
is that a possibility?
Yes, of course. Of course, any expression over any data types, it's a generic precondition. It's not some specific semantic. It's just some expression in some theory and in some Boolean expression.
But still, I can imagine that if you have something like a type system where you can define, encapsulate these properties and say all things of this form are considered cats and all these things are considered dogs. And then in your specification, you can say,
Yes, it's another kind.
but do you have syntax for expressing that?
Uh,
A type system?
Syntax is the generic. If you like to, you can use the simple data types, this integer and boolean.
Mhm.
If you'd like to add your own types, of course, you can create APS. It's a universal data type system based on universal data. You can create but you should have a SMT solver and corresponding predicate transporter. You should invent it for this.
All right.
Any question from the online participants? Well, I guess we can. And thanks again, Oleksandr.
Thank you.